We're going to begin today by talking a little bit more qualitatively about Le Chatelier's principle before bringing back in our Gibbs free energy discussion and seeing how that affects our equilibrium. So we're going to first take a look at the effect of change on heat in equilibrium. So we're starting today on page 38. I skipped page 37 on purpose because that page is actually a duplicate and it shows up later today actually. So we're starting with page 38 in our notes. So example 15, we're going to just consider the following reactions. So this is two equivalents of hydrogen gas reacting with one equivalent of oxygen gas to make two equivalents of water in the gas phase. The delta H for this reaction is negative 483.6 kilojoules. Is this reaction endothermic or exothermic? Well, we have a negative for delta H, which indicates to us that this is an exothermic reaction. So we can rewrite our chemical equation and say that two equivalents of hydrogen gas reacts with oxygen gas to form two equivalents of water vapor plus heat. So heat is considered a product. So which side of the reaction is favored by an increase in temperature? Well, that would shift left towards the reactants, since by increasing the temperature, we're adding more heat. And Le Chatelier's principle states that once you perturb the system, for example here, adding heat, you have to have some sort of rebound in order to re-establish equilibrium. So heat is going to increase, so we have to shift away from heat to re-establish equilibrium. Which side of the reaction is favored by a decrease in temperature? So that's sort of like removing one of our products. So by decreasing temperature, we are lowering heat energy, which would be decreasing the amount of things that we have on the right, which would result in a shift to the right towards the products. In example 16, we are looking at a reaction between cobalt hexahydrate, 4 equivalents of chloride to make cobalt tetrachloride, and water as a liquid. Turns out that cobalt hexachloride is a nice pink color and cobalt tetrachloride is a beautiful purple color. If this reaction were cooled down, which side of the reaction is favored? So we can tell a little bit about the system by empirical observations. So if this reaction's cooled down, it forms something that looks more purple. So that's an observation. So we cool the reaction down, it becomes purple. So is this reaction exothermic or endothermic? Turns out that's enough to make a reasonable guess. So cooling resulted in a shift to the right. So cooling resulted in more purple. That is exactly the same situation as we had with hydrogen and oxygen. If we were to cool this reaction, we're removing a product and we have a shift to the right. We can then say that by cooling the reaction, we get a shift to the right. That must mean that heat is a product, which means that this reaction must be exothermic. So cobalt hexahydrate reacts with 4 equivalents of chloride to make cobalt tetrachloride and water and heat, making this an exothermic reaction. Next, we're going to discuss a system for the dissolution of iron sulfide. Here we have iron sulfide as a solid in equilibrium with iron as an ion, aqueous, and sulfur 2- aqueous also. Iron is a transition metal, so it can have more than one oxidation state, but we can be reasonably sure that this is a 2+ because we can be reasonably sure that sulfur is 2-. Sulfur is in the same group as oxygen. It's a group 6 metal, main group element. And when sulfur gains 2 extra electrons, it becomes isoelectronic to argon, the noble gas. So 2- is a very common charge for sulfur when it's an ion, which means that iron must be 2+. On the next page, you'll find a whole table of thermodynamic properties for select substances, and these select substances are all iron-related and sulfur-related. So in the next few minutes, we're going to pick a few of these values out under our column for standard enthalpy changes. What we may use in the future would be things like delta G for Gibbs free energy and delta S for entropy. From that table, we can discover that the standard change in enthalpy for iron sulfide is negative 100 kilojoules per mole. The standard change in enthalpy for iron 2+ aqueous is negative 89.1 kilojoules per mole, and for sulfur 2- aqueous is positive 41.8 kilojoules per mole. We can use standard enthalpy values to calculate the change in enthalpy and determine whether the dissolution of iron sulfide is exothermic or endothermic using this equation. Delta H is going to be equal to the sum of the products minus the sum of their reactants. So in parentheses, we have the products, iron and sulfur aqueous as their ions. We have negative 89.1 kilojoules per mole plus 41.8, subtracting negative 100. Turns out that this delta H naught is going to be equal to positive 52.7. And that positive sign tells us that this is an endothermic reaction. So this is another way of determining more empirically using values how to determine whether or not a reaction is endothermic or exothermic. Up here, we were using observations. If you cooled a reaction versus heating a reaction, you can get a color change. If you have a difference in color between reactants and products, that is a thing you can do. Would heating the iron sulfide help to dissolve more? Yes, it absolutely would. So given that this is an endothermic reaction, we can add heat to one of our reactants. So increasing the temperature increases the amount of heat energy we have, and that would be a shift to the right towards our products. On the product side, we have all of our ions in solution. So for an endothermic reaction, yes, heating the reaction shifts towards the products. Next, we're going to continue on page 41, which is the example problem that we skipped earlier. So given the following concentrations, in which direction will the following reversible reaction shift in order to reach equilibrium? So this is we are going to be now doing a lot of work to compare a delta G Gibbs free energy to Le Chatelier's principle in terms of which direction a reaction must shift in order to establish equilibrium. So first, we have ammonia reacting with water to form ammonium and hydroxide, and we are given a K, equilibrium constant 1.8 times 10 to the negative fifth. At equilibrium, we can calculate delta G naught under standard equations if R is equal to 8.314 joules per mole per Kelvin at 298 Kelvin. So we can calculate our delta G naught at equilibrium. That is going to be equal to negative RT ln K, which is equal to negative 8.314 joule per mole per Kelvin times 298 Kelvin times the natural log of our K, 1.8 times 10 to the negative fifth. That gives us a delta G naught being equal to 27,000 joules per mole. Now we're going to bank that information because we're going to compare several delta G's to that delta G naught. At pre-equilibrium, we can calculate Q. So Q is the same as K, it's the concentration of products over reactants, except not at equilibrium. So at a pre-equilibrium situation, we could have ammonia is equal to 1 molar, ammonium, one of our products, is equal to 2 molar, and hydroxide, one of our products, is equal to 2 molar. Q is going to be equal to the concentration of our products, ammonium times hydroxide, divided by our concentration of our reactants, ammonia and water. Water does not get included in one of these expressions because water is a pure liquid. What that means is that the reason it's not included is because all of our components are aqueous. The whole background of this reaction is water. So the moment we have some water as a reactant or as a product, it is completely indistinguishable from the solvent that all of this is in. So we have absolutely no idea what this concentration is as a reactant. So we cannot include it. So we cancel it out. What we're left with is then the concentration of our products, ammonium and hydroxide divided by ammonia, which is 2 molar times 2 molar divided by 1 molar, which equals to 4. To rewrite the equilibrium constant K at equilibrium, it's 1.8 times 10 to the negative fifth. So before we're at equilibrium, we drop a bunch of stuff into solution. We have a Q that is larger than K. So Q is too big. So in order to establish an equilibrium, and under which case Q is equal to K, Q needs to get smaller. In order for Q to get smaller, we need to increase our reactant concentration because reactants are in the denominator. To increase our reactant concentration, we have a shift to the left. So in this situation where we have 1 molar, 2 molar, and 2 molar, we have too much product. Our Q is too large, so we have to shift to the left in order to establish equilibrium. Under these same circumstances at pre-equilibrium, we can calculate delta G. We know that this is a delta G at pre-equilibrium because there's no naught symbol. So delta G equals delta G naught plus RT ln Q. That's going to be equal to the 27,000 joules per mole that we calculated earlier for delta G naught, plus 8.314 joule per mole per Kelvin times 298 Kelvin times the natural log of 4. All of that will be equal, show us that delta G is equal to 30,000 joules per mole. So we're going to bank that information and come back to it later. In part B, we see another pre-equilibrium situation. This time with Q is equal. This time we're going to calculate Q if ammonia is equal to 2 molar, ammonium is equal to 1 molar, and hydroxide is equal to 1 molar. We write our Q equation as being the concentration of products over reactants, so we substitute the values in. So 1 times 1 divided by 2, our Q is equal to 5. Q is still larger than K. This is a similar situation. So Q is 0.5, K is 1.8 times 10 to the negative 8, so we still need to shift left to reach equilibrium. For this situation, delta G would be equal to 27,000 joule per mole, that's our delta G naught, plus RT ln Q. So we have R times T, temperature, times natural log of our Q, which is 0.5. All of this will show us that delta G is equal to 25,000 joules per mole. Part C, we have a pre-equilibrium situation, and we're going to calculate Q if ammonia is much, much larger, 2 times 10 to the 6th molar. Ammonium is 1, hydroxide is 1. Q is equal to our products over our reactant concentrations, which is equal to 1 times 1 divided by 2 times 10 to the 6th, which is equal to 5 times 10 to the negative 7. We have a really, really large denominator. We have way too much reactant, so we get a very, very small Q, which is now less than K. At equilibrium, Q is equal to K, so in order to reach equilibrium, Q needs to get larger. Q is too small. So Q gets larger. In order to make that happen, we have a shift towards our products because our product concentration must increase. That is a shift to the right side of the equation. In this situation, we can calculate delta G. Delta G is equal to delta G naught, 27,000 joules per mole, plus R times T times natural log of Q, which is, in this situation, 5 times 10 to the negative 7. This gives us a delta G before equilibrium of negative 9,000 joules per mole. Let's bring all this information together and summarize. In situations where we have Q is greater than K, that's situations like part A and part B. Q is greater than K, we need a shift to the left to the reactants. Q is greater than K, we need a shift to the left to the reactants. In both of these situations, delta G is positive. In part A, it was positive 30,000, and B, it was positive 25,000. We have a shift left when Q is greater than K because we need to increase the amount of reactants because Q is too big, it needs to get smaller. In these situations, delta G is positive. We can read this as a non-spontaneous forward reaction. That means, by extrapolation, that the reverse reaction would be spontaneous. So when Q is greater than K, delta G is positive. What this means is that we have, for a positive delta G going from reactants to products, the forward reaction is non-spontaneous. That means that the reverse reaction from products to reactants is spontaneous, which correlates with the need for our reactant concentration to increase so that Q can be equal to K, and that's a shift left. So all of these things are interconnected. To shift right, this is a situation like in part C where Q is less than K. In that situation, we calculated delta G and it was negative 9,000. That should make sense. So we have a Q which needs to get larger when Q is less than K, which results in an increase in product concentration and a shift to the right. That means that the forward reaction gets a negative delta G. The forward reaction is spontaneous, and the reverse reaction would be non-spontaneous. So in that situation, going from reactants to products is spontaneous, which is exactly the same direction as our chemical shift to reach equilibrium. In our next example, we're going to look at water in the liquid phase versus in the gas phase. So liquid water is in equilibrium with water vapor, and we have a K associated with that reaction, 0.0313. What is the concentration of water vapor under standard conditions when K, rewritten, is equal to 3.13 times 10 to the negative 2? we would write our K equilibrium expression as being equal to our products divided by reactants, but liquid water is always removed. So we are just left with a K that's equal to the concentration of water in the gas phase, which is given to us. It's 3.13 times 10 to the negative 2. We can now calculate delta G naught under standard conditions. So this is the delta G at equilibrium. Delta G naught is equal to negative RT ln K. That's going to be equal to negative 8.314 joule per mole per Kelvin times 298 Kelvin times the natural log of 3.13 times 10 to the negative 2. If we do this math out, we discover that delta G is equal to 8,580 joules per mole. Now, if we change the circumstances and create something that is a very dry situation, non-humid, so we're going to remove some of our water vapor, this would result in non-standard conditions for water, and liquid to gas would not be in equilibrium. So we have now changed our situations into a pre-equilibrium state. So now we have to go to Q and delta G. We're going to calculate Q if the concentration of water in the gas phase is 5 times 10 to the negative third mole. In that situation, Q would be equal to H2O gas, which is going to just be equal to 5 times 10 to the negative third, and it is unitless, so we don't include the molar for Q. In which direction will the reaction shift? There's a typo there. Well, in this situation, Q is 5 times 10 to the negative 3, and K equilibrium is 2.13 times 10 to the negative 2. So Q is significantly smaller than K. In that situation, we need to shift to the right because our products need to be increasing, and Q is too small, meaning our denominator reactance is too large. We are pre-equilibrium, so we calculate delta G. So in this situation, if we need to shift to the right, we would expect that delta G should be negative, right? We would expect that the forward reaction should be spontaneous, which always corresponds with a negative delta G. We can confirm that here using this equation. So delta G would be equal to our delta G naught, which we calculated above, as being 8,580 joules per mole plus 8.314 joule per mole per Kelvin times 298 times the natural log of 5 times 10 to the negative 3. That's going to be equal to 8,580 joule per mole plus negative 13,100 joules per mole, and we get a delta G that's equal to negative 4,520 joules per mole. And delta G is negative, and we have confirmed that the forward reaction is spontaneous. And that's it for today.